All right, awesome. Yeah, so my name's Andy Stokely, and I'm a software engineer at UCAR, specifically in the M-Cubed lab. And yeah, today I'm going to be talking about unit testing Fortran, which is, I know, everyone's favorite subject, and specifically using test-first techniques throughout the software development lifecycle. And then the framework we're going to be using for Fortran unit testing is pFUnit. In case there's any pFUnit developers listening to this, just want to say thanks for developing it. It's made my life a lot easier. Yeah, so anyway, it's going to be like a tutorial style presentation. So I'm just gonna jump right into some code. So imagine that you were tasked with creating a Fortran library that implements it's called a KSGA mutual information estimator, which for those of you who do not know what mutual information is, it's essentially a correlation metric that, not really, but kind of, that allows you to, you can plug it into an actual correlation metric equation that where that correlation metric will then detect both linear and nonlinear correlations. So basically, if there's a correlation, if there are two correlations defined that by orthogonal functions like sine and cosine, Pearson, the normal go-to Pearson R correlation will report that there's no correlation, where the mutual information derived correlation coefficient will show there's 100-ish% correlation. So what does this equation mean? It's not too complex. Here, psi is just the digamma function. N is going to be the number of points in mx and my in those two random variables. It's a k nearest neighbors estimator. So k is the k nearest neighbors coefficient. And nx and ny, we're going to find out what those are right now using pFUnit. So let's see here. Yeah, there you go. I almost didn't include this, but we're going to be using pFUnit for developing this mutual information estimator. And in order to use it, you have to actually know how to install it. So you just go to GitHub. There's good instructions on the it's one of the NASA repositories. So just do git clone, so normal CMake. You can disable some features if you want. And then you just run make install. It's going to put the CMake configuration directory in the CMake build directory, installed pFUnit. And you'll see it in my code, which will be on GitHub. So anyways, and then you just set a CMake variable pFUnit dir to the path to the CMake configuration directory in pFUnit, and then you do find package pFUnit required. Cool. And then also, in order to register a pFUnit test with CMake, all this, the presentation assumes you use CMake. So if you use GNUMake, good luck. I don't know. So the first argument is going to be the name of the test. So in this case, it's test F90 KSG count. The second one is going to be just the sources of the test. pFUnit, like 99% of the code you write is standard compliant Fortran, but like 1% of it is not. And pFUnit does some pre-processing when you compile like your test code, that then converts the pFUnit code to standard compliant Fortran. So that's why there's a .pf versus a .f90 suffix. And then you specify which libraries you want to then link into the test. In this case, test utils and mutual information. Next. All right, awesome. On to the good stuff. All right, so pFUnit supports lots of the standard testing framework features. One of them is fixtures. If you're not familiar with what a fixture is, basically it's in Fortran at least, it's a derived type that then where you can basically define fields in the derived type that then all of the tests are going to have access to. This really decreases repetition, which is, yeah, always great. And then you can then optionally define setup and tear down, subroutines. And what these do is that they run before, setup is run before every test in the test suite. Teardown is run after every test in the test suite. It's important to note it's not run at the beginning and end of the test suite. It's before and after each test. So in this case, we're going to be using MX and MY. Those random variables we're going to create in the setup subroutine. And then these are just the two random variables that we're going to be calculating the mutual information between. So, and you don't have to actually define a setup or teardown method. If not, they're just basically method stubs that don't do anything. All right, next. Great. Test-driven development. So the first part of this algorithm, which I was intentionally vague about because I'm going to explain it through writing tests, is you have MX and MY, and then so can refer to those as marginal random variables, I guess. And then together you can construct a joint random variable. I will call it J. So for example, first entry in J will be first entry in MX and first entry in MY, and so on and so forth. So the first step in the algorithm is for every point in J, we are going to measure the distance between that point. So for example, point JI and every other point within J. So so that's the first step. We're in this algorithm, we're using there's some fancy name for it, for the distance. It's the max norm. It's like the most basic distance measure out there. So we basically define just an array of the distances that we expect, where I'm using very simple input. So I can just calculate these by hand. That's, I think, really important with testing. You could also just use a Python script to calculate these. And then, so these are the expected distances. Then these are going to be the distances I calculate with my subroutine max norm from point. Seems like a pretty good name. So this is going to be the MX, MY, two random variables. These are basically the reference points in MX and MY. Then this is that distance array. And then, pFUnit supports lots of different assert functions, or assert subroutines, I guess. Most basic ones, assert equal. It's the one I use most of the time. So we're just calling assert equal, where we're saying we expect that distances equals expected distances, and it's floating point arithmetic. So we'll give it a tolerance of 1 to the negative 12. And this is the important part that is seemingly strange in test-driven development at first. We're going to make that test fail on purpose. Some people then just compile it without writing any test code, and I work on MPAS Jedi, which takes like 45 minutes to compile. So that's a waste of time. So I just write, at bare minimum, I write a stub so that the code at least compiles. And then I run the test. As expected, the test fails. Maybe some people out there are wondering, why would you ever do this? I could write that code in like 3 lines, which you can. However, one of my very smart colleagues, Jim, pointed out the other day, like it's almost worse to have a bunch of tests that physically can never fail than to have like no tests at all. So this ensures that you are at least writing a test that is testing a property that can actually fail. I've actually caught myself quite a few times, like just literally just testing something that's always true. And then I think my code's right and it's wrong, but all my tests said it passed. So that can give you a sense of false confidence. So anyways, it failed. Now we write, we implement the code that makes it pass. All this code, by the way, will be on GitHub. So just, it's fairly simple code though. And we run the test now, and we're on our way. We know how to calculate the distance between 2 points, I guess. So that passed. All right, next part of this algorithm is going to be, we perform an arg sort basically on that distance array. And the idea here is we're going to want to find the k nearest neighbors to, the k nearest neighbors to that point ji, but we just pre-compute that distance array. So all you have to do is actually sort the distance array, but then sort it in such a way where you're also keeping track of the indices that sort the distance array. It's like NumPy arg sort, if you're familiar with Python. So we just write a stub for it here. And also it's important to note that this is going to be a exclusive k arg sort. So we actually want k plus 1 points, since the sorting operation will include the reference point, which will always have a distance of 0. So once again, I just so it's easy, at least for me, when I'm writing tests, to follow the test, I'm just going to use basically for the input to our k-arg sort test, the distance array we previously computed. And then that way, the tests that kind of tell a story of like how the algorithm evolves. And it's using really simple data. I just find that useful. We'll be using a k equals 3, but since we need to supply k plus 1 to k-arg sort, we're using here a k equals 4. Again, yeah, obviously failed. All right, now we're going to write our code. Again, this code also, it's important to note that test chain development, you're writing like, unless you're like a genius and you just come up with like the fastest, most perfect algorithm right off the bat, you write like, it doesn't matter how fast it is, how horrible it is, you just write code that will make that test pass. That's what I did here. So anyways, we're copying the entire X array. If this is large, this would be really expensive, obviously. And then we are just brute forcing it, where we go loop through 1 to k, and then we loop through all the elements in that X copy. We keep track of the smallest element and its index. We then will set the index of the smallest element X copy to Fortran's version of infinity, basically. And then we store that min IDX in IDXs. It passed. All right. But just because you wrote horrible code the first time around doesn't mean you shouldn't like keep the horrible code around. You should like go back and like make the code better. So that's what we're going to do now. Another thing that's I think important with testing is so I didn't write this actually. I had ChatGPT write this. But the thing is I have a test, right? So, as long as it's allowed, I have no problem having an LLM do my job. I mean, because the whole criticism is, well, like, what if it gives you the wrong result? It's like, well, I'll know that because I have a test for it. So anyways, yeah, ChatGPT came around, and in case you're curious, this algorithm, it's still really simple, but it has the exact same time complexity. But notice how we do not have to make that copy of X here. So same time complexity. However, I did the math. It's like, I think it's a lot lower space complexity because we're not making that unnecessary copy. And then I can confirm that for once ChatGPT was right because my test passed. Awesome. All right, on to the next part. So next part is we're going to have to write a subroutine or function, it doesn't matter, I guess. We're given a list of indices. In this case, it's actually the indices of the k nearest neighbors to point ji we just calculated. We now have to implement a subroutine. We're given those indices, and then given either the mx or my array, we're going to find the distance of the furthest point in that k nearest neighbors list for each of the marginal random variables. So for mx and my. And what this is going to do is it's going to basically tell us, let's see. It's going to tell us that given the joint K nearest neighbor, neighborhood, and J, if we project that neighborhood basically to the marginal random variables, I'm just going to say variables, it's less words. If you project that to the marginal variables mx and my, we're then going to basically measure how similar those marginal neighborhoods are to each other. If they're consistently similar, even if they're not similar actually to the K nearest neighbor's neighborhood, if they're consistently similar and they follow a trend where those neighborhoods increase and decrease at the same time, then that is going to, through a bunch of information theory, I guess, developed a long time ago, that will actually then translate into telling us if they have a relationship with each other. So it's kind of cool. So anyways, yeah, same deal. We write a stub. We know it's going to fail. We pick some very simple input output. We can mentally verify. Write this up. Wait. I messed up my slide. Sorry, I didn't cheat. I did test-driven development here. Well, anyways, yeah, this is, I guess, how you do that. So this is the working implementation. It's very simple. Awesome. Test pass. All right. The next one, kind of alluded to this step in my explaining the previous step. But now we have that radius. We're going to now count for each of these marginal, in each of the marginal variables, how many points are basically within the marginal reference point of that radius we just computed. And that is exactly what this does. So these are values pre-computed in my head. It should be 6. Okay. Yeah, anyways, yeah, I was right. That works. All right, cool. All right, so that's the, I guess that's the subroutine that implements it. It's simple. All right, passed, great. All right, so now all that's left is basically to then create a subroutine that puts all these little helper internal subroutines together. So it just completes a entire iteration of this step in the algorithm. So that's what, again, I can compute these in my head, and then that passed. And so this is the code that implements that. So that passed, and I'm not refactoring here because this code's actually pretty good. So, and great. So, and that is, and then I create a subroutine that then basically, calls the F90 KSG count subroutine just in a loop, so that we're able to compute all of those NX and Y counts just with one function call. That's what that code looks like. Best pass. All right. So with that, we just use pFUnit to create a test suite for, so this algorithm has about a 2-page math proof on it. And I would make the argument that using test-driven development, breaking up into very small pieces, writing tests to verify each piece works, and at the end testing the behavior and the interactions between those pieces, also took 2 pages worth of math with Greek symbol, all that stuff, and turned it into about 100 lines of code where the most complex operation is sorting an array. And if you actually looked at the math behind this, you would never know. And at least for me, if I tried to, I guess, kind of write the code, without tests, I'd probably write all jumbled together, and it'd be very hard to understand, very hard to verify I didn't make a mistake. But by breaking up into pieces, using tests, using pFUnit, then it really helps out there. And so now we are going to basically finish implementing the actual subroutine that calculates the mutual information, create a fixture, same thing as last time. And create the stub for the function. And what's interesting here is I've noticed this a lot working at UCAR. I previously worked at UCSD and then also worked in private industry and drug development. Is that there's this like bridge between like the scientists, right, and the software engineers, where it's really hard. I feel like sometimes it's really hard for the two groups to communicate with each other, especially when it's complex math. So this, I think, really helps improve that communication. And then the other thing I've noticed is it's like, okay, great, Andy, like you just wrote 100 lines of test code that shows you know how to like count and sort an array, but you know, how do we actually know the mutual information is correct? Like, how do we actually test that, right? Because if it's wrong, it's going to be hard to detect. It's floating point arithmetic. And the most complex part of that algorithm, we just wrote tons of tests for, and that's actually integer arithmetic. So we're able to verify without having to use floating point tolerances that's actually correct. And I think that came out by using test-driven development here. And then instead of actually testing like exact values for the most part here, what we're going to do is we're going to actually test the properties. I'll show you how to do that with pFUnit. So we're going to test the algorithm properties. In this case, they were mentioned in like the results and discussion. So it's like the plots with like all the stats, you know, the trends, if you, for this, blah, blah, Gaussian, if you increase the K, then the mutual information estimate should do whatever, should decrease, stuff like that. If the two variables are independent, then it should be roughly 0. If they're perfectly correlated, it shouldn't. That kind of stuff. So yeah, so some people call these, I think, metamorphic tests, or I just call them property tests. So for the generating random arrays, I just write all these tests first. And this is very simple with pFUnit. It's just, I'm just writing a subroutine, calling assert equal. It's auto-registering with my test framework. It's great. So this is I won't go into how I do this. I wrote some helper math routines. But this just generates two random variables, mx and my. And if the algorithm is implemented correctly, then this test should pass. However, you'll see this in a second. Just because this test passes doesn't not mean the algorithm is correct at all. All these tests are working together. I purposely was fuzzing this thing with like bad data, and actually generally most of the time 80% of the tests would pass. But the thing is it just depends how I fed it bad data or what line of code I commented out. That would then kind of dictate which test passed, which is, I think, really cool. It goes to show you they all kind of work together, I guess. So in the literature, what it says is they provide like error tolerance math and all that fun stuff. The idea is when you take a fairly large random variable, I think in this one I'm using 1024 points. You calculate they're independent, and then you set the K value roughly equal to 1024 over 2, so K equals 512. The mutual information here should, roughly speaking, be 0. This is unfortunately kind of a pricey, I have a high tolerance here, because if the K value equaled n, then it would be 0, like within like, it would basically be 0. But since it's expensive to perform this calculation, I set equal to 512, so it runs way faster, and I'll still get an idea of if this property probably holds. Next test, and I wrote this math helper, in a different module, so don't worry about that. But paper also mentions that if you have a correlated Gaussian where the x and y dimensions are going to serve as our mx and my random variables. Let's see, what's this thing have? I think it's 0 mean, unit variance, 0.9 covariance. Yeah, and then it gives you this ratio of k's. So I did the math. Basically, if k is over 4,000, and then you multiply it by 0.04, and then you add 0.05, was in the paper, then roughly speaking, it should be fairly close to the analog solution, 0.05. Tolerance I calculated with NumPy. So that's another test. And yeah, so Gaussian ratio. So this is, I already kind of mentioned this. I do the same thing as the previous test here, except according to the paper, when you, let's see, increase K in this way, using these numbers, then MiO2 should be larger than MiO4, and then that should be larger than MiO6. So what's really cool with this one is, remember that last test, I was having to use 4,000 something points. I'm back to using 10,024 here. So this is actually a way more powerful test. The other one makes sure that I'm testing properties that are like kind of in the ballpark of what we expect. But this test is, it's using a lot less data, so I can create a much more powerful test here. So assert true. Oh yeah, and then as usual, because I guess love wasting compute time, I compile this stuff, everything fails. Yeah, see, and then I don't know if I actually pointed this out, but cool thing with pFUnit is when a test fails, it is giving you the line number. Like, that's awesome. It's like, you get down like Python or Rust or C++ or something with exceptions, not in Fortran though. So it's doing this with its preprocessor, injects some introspection code, I guess. But so it's telling me the exact line number, my test suite where this failed. It's pretty, I just didn't allocate any memory, so I guess the compiler decided to zero out everything, so that's pretty expected. Yeah, so all my tests failed. And then I'm not really even going to go into, honestly, the math behind this. If I found someone's Python code online that actually implements those algorithms, so I that's what I'm kind of basing, that's what I'm basing my digamma estimations on. And then, yeah, I just call, where is it? F90KFP counts. It's the code we just wrote. This is just so this is an average digamma sum. You saw it on the first slide. And then these are just the digamma K, digamma N. I'm adding 1 because the algorithm assumes 0 indexing, but we're in Fortran, so yeah. And then, oh my gosh, all the tests pass. This is great. And then there's a correlation coefficient I was talking about. It's pretty simple. I followed the exact same procedures for that. So here I'm generating those independent arrays. Like mutual information when random variables are completely independent is going to be 0. Same thing with the correlation. This one's kind of interesting. I'm pretty proud of this one, actually. So one of the properties of this generalized correlation is it's never going to be negative. It'll always be bounded between 0 and 1. So Pearson correlation actually can be negative. So in the case where you are measuring correlations with correlated Gaussians, if you use a negative covariance, the Pearson correlation will be negative, and the generalized correlation will be equal to the absolute value of the Pearson correlation. So again, here, I'm actually not, as you can see, I'm not testing really any precise floating point arithmetic, just making sure these two values cancel out. So that makes it, the tests a lot less flaky, I feel like. Nonlinear, yeah, so this is good. Okay, so one way to generate, I guess, nonlinear, perfectly correlated nonlinear random variables is just you just feed data into sine and cosine functions, and then basically output from those is going to be perfectly correlated but nonlinear. So I just want to make sure that I'm getting perfect correlation detection in that case. and I haven't written any code, so all that stuff fails. Wrote some code. It's really simple. You just calculate mutual information, do some standardization stuff, and they all pass. Oh yeah. So this is great and everything, but unfortunately, I think your HPC admin person would be like kicking you off the compute nodes if you use it, because it's like beyond slow. Like it's really slow. So I enjoy CUDA. I like writing C++ CUDA in my free time for some reason. So I decided to implement the algorithm in CUDA, which I won't show you how I did that because it's pretty difficult. But just because I'm working in C++ does not mean my pFUnit tests are useless. In fact, when I wrote C++ tests, but I just used ChatGPT to convert pFUnit tests to C++ ones. And then I just had to convert my Fortran to C++, and all the tests passed. So it actually worked really well. It took like 2 minutes. So I myself didn't have to write really any extra tests when doing this vastly different language port. And the algorithm is completely different. And it was so flaky and error prone. With all of the red block synchronizations, I had to completely rearrange the sorting in a strange way so that I didn't have to use GPU sorts and all that fun stuff. It was 1,000 times faster though than the CPU version, which is great. But all I did was basically, because I already had Fortran tests in place, I had, in my opinion, pretty well organized decoupled code from using test-driven development. I was able to then just write a interface first for C++ and then CUDA using the same signature as my F90 counts interface. I then just was able to add a optional procedure interface argument to calculate mutual information. And when you provided that, so that was just going to be like the KSG counts strategy. Technically, it's a strategy design pattern if you're into design patterns. And by default, if you didn't give it a strategy, it would just go back to F90 KSG counts. So it didn't actually break any implementation, and this is awesome. And if I would not have been writing this with testing in mind, we've all seen the Fortran code bases, we would copy and pasted it. We would duplicate all the code. So the hot path is just the KSG counts. I'm able to actually reuse Fortran mutual information, generalized correlation, and my entire Fortran testing suite. I did not write one test for the CUDA specific code. I'm testing it completely through that Fortran interface. So that was great. Anyways, but you're probably thinking, oh no, you're going to have to copy and paste in all your whatever tests, because how are you going to tell the test suite to, or you're going to have to, write a new test for each backend, but not pFUnit. Nope. pFUnit supports test parameterization. PyTest does this. I use Google tests sometimes. They do it though. Their macros suck. Anyways, so this is pretty common in most modern testing frameworks. So what we do here is we define, it's called an abstract test parameter. It's a built-in pFUnit class provides you. So you don't define it, you extend it, I guess. You are required to provide a few different things. One is a name. So you're going to give a name to your parameter. And the parameter in this case is going to be the KSG counts strategy. So I'm providing a procedure interface, I guess, pointer for the parameter. The name is going to be the backend, so Fortran, C++, or CUDA. And then this derive type is required to override an abstract type-bound method called toString. This is used by pFUnit under the hood to basically generate a different test name that is for each of your parameterized test cases. It's very similar to just a normal test fixture, kind of. You're extending a parameterized test case, and then you're going to define so type KSG account strategy param. So that's the thing we just talked about. Here I'm going to provide endpoints just as before. So 1024, my MX and MY. We also just provide setup and teardown methods. And then here what we're doing is we're providing a factory function that's going to serve basically as a like a derived type constructor, but Fortran doesn't have those. So we have to create our own factory function. And then we have to implement a getter that then pFUnit can use to then get those test parameters. So that's what this is. And then just to make it feel like I'm coding in, I guess, an OO language, I can just override the name of that factory method, the name of the derived type. So it actually acts really similar then to a normal constructor. Yeah, and then so the factory is just going to basically be the thing that then just the function that then creates that the parameter, and then get count strategy params will just be used to then get the parameter, and then for every one of those tests in my previous test suite, pFUnit will generate a test for each of those parameters. So I will have a test at my disposal for Fortran, CUDA, and C++. Another cool thing, because I have a MacBook and a Linux desktop, I can't run CUDA on my Mac because, you know, doesn't have an NVIDIA GPU. So because you're concentrating all of this information about which strategy you want to use in your tests in like one spot, you can use compiler preprocessors to basically add the CUDA test. So if I'm on my MacBook, I can compile CMake with a CMake variable, just name like I don't know, disable CUDA, and then define something else called CUDA support. And then if that's defined, then it compiles and runs the CUDA test, which is pretty cool. And then I'll just show you one test. So one test is just the first one. So all I did was so now we're going to have this now has, remember, the param. So this param KSG count strategy, and I generated this on my MacBook, so I wasn't running CUDA. Oh no, cut off my last slide. No, it didn't. All right, see, and then this is what pFUnit automatically does. Is see, it generates the test for Fortran, and then it generated that test with for C++. It has more features that related to MPI, but I know nothing about MPI really, sadly. So I'm the wrong person to give that, I guess, presentation or tutorial. So anyways, yeah, that's it. Yeah.
Thanks, Andy. Yeah, if anybody has any input questions for Andy, just feel free to unmute, put your hand up, I guess, if we get a lot, but otherwise go ahead. And Andy, if you have any questions for the audience, you want to prompt conversation, go right ahead.
Just to mention, I guess, a few things. I was going through this code this morning, and I think I did test coverage at some like 97% or something like that. That's crazy. And I was still able to break it super easily. In fact, I actually found a bug in it where it allows you to calculate, get the digamma for 0, which is undefined. So yeah, I just wanted to point out that just because it has tests doesn't make it like perfect. But then when we find those bugs, when we refactor, when we fix them, we add more tests to prevent them from happening again. And then we can make sure we didn't break the code when we're fixing it. That was the last thing I wanted to mention. So yeah, that's it.
Cool. Maybe you can stop sharing. So yeah, we can just have cameras up.
Yep.
I guess I have a kind of a generic question, but I'm curious because I've never used pFUnit, but I have used things like PyTest. What would you say are its particular strengths and if there are any weaknesses compared to other like common, testing frameworks that people might have experience with?
Yes. So strengths are definitely going to be, it's very easy to implement like parameterized tests. It has very good support. It overloads those assert subroutines for basically every built-in Fortran type. I didn't really show it, but it allows you to do custom messages for asserts and stuff. To my knowledge, it's the only Fortran testing framework that then will generate essentially like a traceback for errors. So it actually tells you where the error was in your test file. So it's like sometimes you should probably have one assert for test, but sometimes I have like 10 because, I'm lazy sometimes. And I don't have to actually even write a message. Like I don't think it wrote any messages there. So that's pretty sweet. It generates auto messages. Weaknesses, in my opinion, I would really like it to actually be Fortran. I think when your test isn't something that's actually even really executable without a preprocessor, I think that's a weakness. It doesn't work out with NVHPC. What does? I'm just kidding. No, so I mean, but that's a big weakness because it's like if you're using OpenACC or especially, or I was originally going to write like the CUDA for it in CUDA Fortran, and I had to use C++ because there's not. So that's a weakness. But yeah, so I would say environment support and lack of being pure Fortran would be its weaknesses.
Thanks. Yeah, and I see Eric mentioned as well program abort testing.
Also, you have to use CMake. It forces you into a build system. I kind of think that's a good thing because it makes it so everyone doesn't use their own favorite build system. But still, for example, impasse is in GNU-make. So it's like we could realistically never use pFUnit with GNU-make. That's definitely a weakness. Yeah.
All right, Andy, do you have any other questions for the audience, or looks like Matt, go ahead.
Oh, I just wanted to say that I think there is sort of GNU-make support in pFUnit, but it's not very well tested. I think it was asked by someone long ago, and we realized CMake was the way forward sort of thing. But if a user needs it, we could probably figure it out. But I think at the moment, yeah, CMake. I mean, it could even be gone at this point. I don't know. It's possible Tom removed it. But at some point, there was some mild GNU-make support in there, like pure GNU-make.
All right, I think we did have a general idea of if anybody wants to bring anything up related to Fortran unit testing in general, any observations, experiences, questions for the crowd, anybody can jump in. Or if you haven't done it, and you could talk about why. Yeah, Dom.
Hey, this is a bit of a follow-up on the previous question, how this compares to other unit testing frameworks. There is this Julian framework that Berkeley Lab has, and I was wondering if you have compared those two, what you think of Julian versus pFUnit.
I had no idea that existed until just now. So no, I have used yes, pFUnit. I have also used the one that's officially supported by the Fortran package manager. I forget what it's called, but yeah, pFUnit though it just also seems very tailored to HPC. And it has extremely good support for MPI. I didn't talk about that, but it allows you as a lot, and all of those asserts are going to be blocking for MPI, and they're blocking for OpenMP. So that adds a lot of support for writing distributed parallel code. You don't have to worry about, and yeah, handling synchronization around assert messages, which is pretty cool.
Okay, that's good to know. Thank you.
Yeah.
If,
Blame the
if
top
I
guy.
remember, oh,
Is it my turn?
oh yeah, go ahead. Go ahead.
Oh, okay. Yeah, sorry, I didn't mean to interrupt. Good to see you, Andy. I'm Andy's former coworker, and I
Oh.
definitely feel out of my element here. I'm primarily a Python coder, and so I'm kind of a high level programmer compared to the, you know, in the my knowledge of C++ and Fortran certainly is minuscule compared to this crowd. But I do write unit tests, and I just wanted to get your impression and anyone else who would want to speak up. How much do you trust AI to help you write unit tests, or to the extent that you just like outsource it to there? Because I've had mixed results. In my experience, AI has been, I can't quite trust it to just go off and do stuff without expending precious mental resources to like double check its work and make sure that it's not just being lazy and generating pointless unit tests. What's your sense about that?
So I always write, I wrote every single pFUnit test. I actually wrote them in my car, in a car ride yesterday without internet. So there was no AI there. And I would only be comfortable doing direct refactors, which I really did. I did copy and paste from ChatGPT for my C++ unit tests. But that is because I'm feeding it in pFUnit unit tests. And I'm able to verify that those tests and my hand rolled tests are testing the same behavior. It did make some mistakes with C++. It was calling like stud move on strings, which was causing weird memory stuff in maps or whatever. It completely butchered CUDA. It has no idea how to write CUDA, so that's good for job security. So I think you have to trust it when you can immediately verify it with knowledge that you have yourself.
Very good. Thank you.
Yeah. And Eric, were you saying something? Or no?
Oh, I was going to say something, but now I forgot what I was going to say. Let's see, before this, we were talking about Julianne a little bit. But yeah, it looks like from what I could tell, they had a tutorial on Julianne at the ISS conference last year. And it looked, you know, like a lot of things were similar to pFUnit. And since we were using pFUnit, I remember asking some of the speakers at LBL about, you know, should we convert to Julianne, you know, and there didn't seem enough of a reason to. It did seem like, if I remember right, it was easier for Julianne to like just run a subset of the tests. And that was harder in pFUnit. But that's about the only thing I remember. So.
Does anyone have any thoughts on, I wasn't trying to overly complicate the presentation. Originally, I think it was like, you know, some classic foobar shape or car engine example or something. But I tried to use a numeric example to show that unit testing can be used. And these techniques can be used when doing scientific numeric development, just slightly differently. But I kind of noticed that they are not used really at all, at least from my experience with scientific code bases. So if anyone has input on like why that is, yeah.
I have a different point, but I think it's maybe related to something you were saying about MPI. So we're recently started unit testing or pFUnit to do unit tests in a project. It seems like each unit test in pFUnit, they don't spin up their own instance of MPI. So like they'll bundle them all together. Have you found a way to maybe get around that? Because I think that would help us out a little bit. If we could basically do like a test harness that does an MPI initialize and finalize, and then we run a bunch of unit tests outside that, so we're not sure the same state.
No, I know exactly what you're talking about, and yeah, no, it's a little frustrating. I spent like a weekend writing my own unit test framework just to get around that, but just for fun. But so a few things I have noticed, and this is not perfect in the slightest. A few things you can do is it leads to probably leaking MPI resources, but what you can do in that setup is you can check to see if MPI has been initialized. So then at least that way, because I think what you're talking about right now is if you have a testing environment where you want to call MPI init once, there's no really great way. We have that in MPAS. There's no great way to do that with pFUnit, because you then call MPI init, and you can't call that again until you call MPI finalize, but you can't actually then call MPI init again because it's in the same executable. So what that leads to is, these are more like kind of integration tests, is then having to like write like one pFUnit test suite, like per test, which is kind of, in my opinion, a waste of code. So
That's what we're doing now. Yeah.
For more complicated tests like that, also maybe just writing Fortran programs, and then registering those with like CMake. And then use pFUnit for more of the fine-grained unit tests that are not, yeah. It's not perfect, but yeah.
Sorry, because my turn. Yeah, just to your first off, great presentation, Andy. I was just kind of responding to your kind of question of like, why are we doing more of it in science codes? And I only speak to what I work with, but I noticed for a lot of legacy Fortran codes, like I run CAM, which is code from literally is code from the 80s. A lot of the Fortran design is such that it kind of sharing a lot of module, like you have a ton of use statements, and then they use other modules that then use other modules, and so building something just to run a unit test ends up being this huge effort. And this was, and especially pre-season. Yeah. So, which actually, so for us, like we've implemented Michael Waxman, to get credit because he'd set it up for us, and Quan Chi Wang, who are on here, but it's been good for us because then by writing tests, it's forced us to modularize our code more than it was previously, and so I think it's helped us. And so it's hard. So I think there's like this initial burden, which is hard to get the test set up, but then I feel like our code, even beyond everything you shared, I think just our code is now better because it's modularized in a way where unit testing is doable. So I might be preaching to the choir here, but yeah, but I definitely know that was a big burden for us. It's just our code wasn't set up to easily build in an independent fashion. So yeah.
Yeah, I worked on a legacy Fortran project. And it was kind of like the same thing where it's like, oh no, we got global like allocated linked list pointers or whatever all over the place. And yeah, my workaround for that was taking a deep breath and then just using like PyTest, with sub processes, and then at least like gathering, just saying it to netcdf files or whatever, and then at least I had a validation test suite. And then every bug I would find, I would then write a pFUnit unit test for it. So if you look at that repo, it's like, why are you testing for like the transpose of a matrix? It's like, oh, that was a bug I found. So yeah, definitely you have to take it piece by piece, I feel like, with the big repositories.
All right, well, Jesse, if you don't have a follow-up, we are at the top of the hour. I want to be respectful of people's time. So I'm going to cut the recording now, but I guess if anybody wants to stay on and continue conversation, that's totally fine with me. But just give Andy a thanks for suggesting this topic, presenting, inviting a few folks, and getting the conversation going. So thank you.
yeah, I'm gonna jump off. So yeah, see you guys.
All right. Thanks, Andy.
Thanks, Brian, for setting it up. Have a good one.
Yep.